Now we are going to look at something about the equations of motion. Equations of motion are those which govern the motion of a body when it is moving along a straight line. And even in case of the two-dimensional motion, these equations of motion can be used provided the velocities or accelerations are to be taken in their respective components. Here our discussion is restricted to the equations of motion pertaining to the straight lined path. Here these are the four equations of motion which we have. We have discussed something about these equations of motion in our earlier classes. These equations, if at all any three parameters are known, the fourth parameter can be easily determined. That means using these equations of motion, these are the relationship between displacement, velocity, acceleration and time. So if any other three parameters are given, the fourth parameter can be determined. Now how these equations can be determined, how these equations can be derived, the derivation part we are to look at, and also how these equations can be applied in case of a body moving under the influence of gravity. Here in case of the influence of gravity, the A is taking G, A is taking a value of G. Those equations we will look at once the derivation part is done. First, the derivation of V is equal to U plus AT. Derivation of V is equal to U plus AT. Here, how it can be derived? First of all, let us consider a body starting with an initial velocity u and attains a final velocity v after time t. The acceleration is given by A for the body. Here these equations are valid for uniform accelerations only. If the body is moving with non-uniform acceleration, these equations are not valid. Therefore, according to the definition, A is equal to uniform acceleration is given by change in velocity by time. So here A is equal to final velocity minus initial velocity by time. Rearranging the terms, AT is equal to B minus U. So V is equal to U plus AT. This is going to be our first equation of motion. So this is how the very first equation can be derived. Now we are going to look at the equations of motion which govern the motion of a body. So these equations can be used either for a straight line path or for the parabolic path, etc. So these equations play the vital role in determining the various parameters of a body during the motion. Here these are the parameters which have already seen, that is displacement, velocity, acceleration and time. And these equations correlate all these three parameters. And they are four in number popularly. V is equal to U plus AT, S is equal to UT plus half AT square, V square minus U square is equal to 2AS, Sn is equal to, that is distance travelled in nth second, is equal to U plus A into n minus half. Here if any parameters are known, then using any of the equations the unknown parameter can be determined. Then how do I arrive at these particular equations? First, let us start with the derivation of V is equal to U plus AT. Here We are just considering that a body is starting with an initial velocity u and attaining a final velocity v after time t. And moreover, you need to remember that these equations of motion are valid only for the body moving with uniform acceleration. Therefore, the uniform acceleration of a body is given here as a. In such case, according to the definition of acceleration, acceleration can be defined as change in velocity by time. So here, final velocity minus initial velocity divided by time gives rise to the acceleration. Rearranging the terms, I can come to a conclusion that final velocity is equal to initial velocity plus the product of acceleration and time, that is v is equal to u plus at. This is going to be the first equation of motion. Now we'll define the first equation of motion, that is v is equal to u plus at, graphically. Here, let us consider a body is moving with an initial velocity u and reaching a final velocity v after time t. If at all I draw the vt graph for that, it is going to be a straight line starting from some point, because it has an initial velocity u and reaching to a final velocity v here, and time taken for that is going to be t. So this is a time taken starting at an instant 0, and after time t, at 0 instant the initial velocity is u and at time instant t the final velocity is v. Then according to definition of acceleration, a is nothing but a is equal to slope of vt graph. Therefore, a is equal to, when I take the slope here, this is going to be v minus u and this is going to be t minus 0. Therefore, if at all I substitute the value, slope is nothing but y by x. Y by x is nothing but v by u minus v minus u divided by t minus 0. That is giving rise to a is equal to v minus u by t, simplifying v is equal to u plus at. This is how v is equal to u plus at can be derived graphically. This is the derivation of v is equal to u plus at graphically. Now we will derive the second equation of motion, that is s is equal to ut plus half at square. So here we'll just consider that a body is starting with an initial velocity u and is moving with an acceleration a, then reaching the point, another point which is at a distance of s after time t. Its initial acceleration is a, which is constant, because these equations are valid only for constant acceleration. So the parameters given for us are initial velocity u, constant acceleration a, and the distance traveled is s in time t. These are the things given to us. Then we need to get the relation between distance traveled, initial velocity, acceleration and time. For that, we have the distance traveled expression as s is equal to v average multiplied by the total time taken. Here v average can be taken as s is equal to v1 plus v2 by 2 into t. Here v1 is nothing but the initial velocity, that is u. v2 is nothing but the final velocity, that can be written as u plus at by 2 into t. So here when I simplify, I will be getting 2 ut by 2 plus half at square. When I simplify, I will be getting s is equal to ut plus half at square. This is going to be our second equation of motion. So look at here, Whenever we are going to derive s is equal to ut plus half at square, let us consider a body starting with an initial velocity u and constant acceleration a is traveling through a distance s in time t, and we need to get the relationship between all these four physical quantities. For that, we have the distance traveled by a body as the average velocity multiplied by the time. Therefore, here the displacement can be written as displacement or distance. Whenever a body is moving along the same direction, distance and displacement are going to be the same. Here, average velocity can be given by v1 plus v2 by 2, initial velocity plus final velocity by 2 multiplied by the total time taken. Initial velocity anyhow it is given, that is u, and final velocity using the first equation of motion, I can write the final velocity as u plus at. Substituting the values and simplifying, you can get here ut plus ut, that is 2ut divided by 2, and here at into t, at square divided by 2. Simplifying that, you are arriving at s is equal to ut plus half at square, which is the second equation of motion. Now we are going to look at the derivation of the second equation of motion, that is s is equal to ut plus half at square, in a graphical manner. So always the graph is going to be VT curve, time versus velocity. So when I look at the velocity time graph, here time is taken on x-axis, velocity is taken on y-axis. Here we are supposing that a body is moving with an initial velocity u and reaching to a final velocity v after some time. Now here it is the 0 instant of time, and at time t it is reaching to some other point. So this is after time t. This is the time axis and this is the velocity axis. Here the area under the graph, area under VT graph, V versus T graph, gives the displacement, So here area under the graph can be calculated as, if I name them as, this is the point O, A, B, C, then area under the graph can be taken as area under, so this is the point, this is the area under this rectangle, and this is the area under, this is a trapezium you have, O, A, B, C, D. So I can write here area under rectangle OABD plus area under triangle DBC. Here I can write S is equal to here it is time and here to here it is u. So area under rectangle OABD can be written as u into t plus area of the triangle can be written as from here to here base half into base into height. Half base is time and height is going to be v minus u, because it is starting with an initial velocity u and reaching a final velocity v after time t. So this is going to be v. So this difference is going to be v minus u, and using v is equal to u plus at equation, v minus u can be written as a into t. Therefore, substituting v minus u value here, s is equal to ut plus half into t into, in place of v minus u I can substitute at. Therefore, at when I write over here, S comes out to be ut plus half at square. This is going to be the derivation of second equation of motion in a graphical manner. So this equation can be derived in this manner. See here, you just take a body starting with an initial velocity u, moving with constant acceleration a, so that after time t it will be reaching a final velocity v. If at all I draw the vt graph, the vt graph is going to be a straight line starting from certain point on the y-axis. So the graph is going to be like this. If at all I take the area under the vt graph, that area under the vt graph is going to be the displacement travelled by a body. Therefore, area under vt graph gives the displacement, which means the area can be sum of the area of this rectangle and area of triangle over here. Therefore, S can be taken as area under rectangle OABD. I am just denoting this with some notations, and here area under triangle DBC. So area under rectangle can be taken as u into t, because this parameter is t and this parameter is u into t, and coming to the area of triangle, this parameter is t and this parameter is v minus u. Therefore, half base into height is the area of triangle. So half t into v minus u. And already we have a knowledge about v is equal to u plus at. Therefore, v minus u can be written as at. Substituting that value over there, S is equal to ut plus half into t. In place of v minus u, I am substituting at. Therefore, S is equal to ut plus half at square. That is going to be the equation.